Okay, so this is kind of the whole package for discussion of a discretization scheme in general, right? We just went over the whole package for the simplest discretization scheme, finite difference. Also for the one of the simplest equations, we can analyze the heat equation. But this procedure and also many elements of what we went through during this procedure actually applies very well to other discretization schemes and other differential equations. The procedure includes, first of all, we have to figure out how to approximate the derivatives, how to convert the partial differential equation into either a system of equations you can solve in a computer, a finite set of equations, or into an ordinary differential equation or system of ordinary differential equations. Either way, we already know how to solve that, right? So that's the first step. The second step is figuring out during this approximation, during this conversion, how much error did we commit? How much error did we make? And here we use the Taylor series analysis. We derived the order of the scheme, which is very important in many, in basically all the schemes you are going to look at. And the third is to analyze basically the stability of the scheme, because the stability of the scheme actually impacts how much of the approximation error would translate into the solution error. It may not be that obvious in this equation, and it's still important in this equation, but it's not that obvious because as long as you satisfy this criterion, okay. So let me say it another way. It's not important for this equation if you use ODE45 to integrate it, because if you use ODE45 to integrate it, you can kind of assume you're actually solving the ordinary differential equations exactly. If you're solving the ordinary differential equations exactly, what you should be, the stability criteria you should be looking at is the stability of which equation? Of the semi-discretized equation for which the solution is this, right? And this is always stable. I mean, it may not be as stable as the original differential equation, but at least it's always stable. It's not going to be blowing up, right? So for this is if you use OD45 to solve it, it's not that obvious. But if you use forward Euler to solve it, you feel the impact of stability. If you don't satisfy the stability criterion, your solution is going to be blowing up very quickly. In some other equations, you are going to see the difference a lot more severely. In the next equation, the advection equation we are going to be looking at, the stability actually is more trickier to satisfy and enforce than in this equation. Okay, so these three things are the three things we are going to be looking at for all the other equations and the discretization schemes. Okay, any questions? Yes? That's right. We haven't incorporated because we have been looking at the equation that is not that for which kappa is equal to 1, right? So let's actually let me see if what color should I use. If I just use let's say purple. Okay, so if I introduce a kappa in this equation, what difference does it make? So if I introduce a diffusion coefficient in this equation, I would have a kappa over here, right? And if that changes, what I'm going to have is I would have a kappa over here and a kappa over here and a kappa over here, right? So basically the exponential decay coefficient is going to have a kappa on top of it. So similarly for the analytical equation, the rate of decay coefficient is having a kappa over here, and So, of course, the two sides are going to be multiplied by kappa. We have kappa over here and kappa over here. So then in the final analysis, this is going to be having a kappa over here and a kappa over here and kappa over here, right? So in order for this whole thing to be e minus 1 and 1 to satisfy the criterion, we need to multiply a kappa over here. So the final stability criterion has to be delta t over delta x squared times kappa less than half, which means the stronger the diffusion coefficient is, the more severely I'm limited in the time step size. Also, the smaller my delta x is, the more severely am I limited by the time step size. Yes?
So can you construct the left-hand side for the conventional analysis of the so we're putting the part out of the analysis for one half.
Yes, that's right. That's right. So kappa has a dimensionality of basically the spatial dimension squared over time dimension, right? So this is if they are restricted to delta t and delta x, so if I would say that if you know kappa is going to be proportional on the left hand side, and you're only allowed to use delta t and delta x, the only non-dimensional thing you can construct is this, right? But it's not obvious from the beginning that the kappa has to be different. Okay.